Alright, hello class. In this lecture we're going to be continuing our discussion about line integrals over vector fields. I'll consider this part 2 of this particular discussion. So there's really two things I want to add to the discussion. So this one probably won't be as long as the first part. We did most of the heavy lifting there, but I do want to talk about the other type of line integral that's out there, and I also want to sort of serve as a bridge to the next topic, which is conservative vector fields, which I hinted at a little bit before in the last video, specifically in regards to vector fields that say push just as much as they pull, for example, along your path, and how those act in regards to line integral. So let's get... Alright, so the second type of line integral is actually the flux. So the flux over a path C. This, instead of measuring how much of the field pushes with the path, or say against the path, this measures how much of the path is, or how much of the field is perpendicular to the path. Okay, so for example, with the circulation, what we did is, say we had our path and we had our vector field. Let's say here's our F, it's behaving this way. All right, however it might be acting. And for the circulation, we compared it to T. Right? So T gives us the direction of travel. Well, what we're going to do for the flux is, instead of comparing it to T, we're going to be comparing it to what we'll call N, which is the unit normal vector. So we want a vector that is normal to T. Okay, so instead of with the circulation, we had the line integral of f dot t ds. What we're going to look at for the flux is instead the line integral of f dot n ds, where n is a unit normal vector to t. So, okay, so we want n to be a unit normal vector to t. So, well, you might be wondering, well, which n are we talking about, right? There are two unit vectors that are perpendicular to t, right? For each little n I drew here, I could draw another one that's the negative of it. So which one are we talking about? Well, for convention, what we do is we set it up such that the way I like to think about it is, if we create a path that's counterclockwise and encloses a region, we want the n that points outwards for this. All right, so to write that down for you, that if C is a closed counterclockwise path, so this is closed counterclockwise, enclosing a region R, how we want this set up is that all the ends should be perpendicular to the path C and pointing out of the path. That's what we want. Okay, so we're talking about the outward unit normal. Okay, now what happens if, we have something like this where we don't really have maybe a way to talk about what's counterclockwise or not, or maybe it's just a straight line. The definition that we do is we use this vector. We take n to be the cross product between k and t. Okay, so we want n to be t cross k. So by the way that So remember, k is always pointing out in the positive z direction. So based on the right-hand rule, with how t behaves, so here's t, by the right-hand rule, this is always going to produce the vector in the direction that we want. So what the cross product of t cross k gives us, if we can remember how a cross product works, I know it's probably been a while. Okay, well t, I'm going to say t is the vector t sub x comma t sub y, just to simplify some things for us. So in 3 space, it's going to be t sub x, t sub y, 0, and the vector k will be 0, 0, 1, and we will copy this down over here. And so we will get, in our I component, we're going to get the main diagonal will be t sub y minus 0. And then for j, we'll get 0 in our main diagonal, but minus t sub x in our off diagonal. And then for the k, well, k is going to be 0 minus 0. Right, so we don't have a k. So what we end up with is back down to a two-dimensional vector. We get the vector t sub y comma negative t sub x. Okay, so what ends up happening is if t, well, that's, if we have it as r prime over the magnitude of r prime, right, that's going to be x prime over the magnitude of r prime, comma y prime over the magnitude of r prime. Okay, so that means n is going to be, well, we're going to swap this around. This is our ty, this is our t sub x, so we swap. We're going to get the vector y prime over the magnitude of r prime, comma negative x prime over the magnitude of r prime. Okay, now this might seem complicated. However, when we get down to our flux formula, so let's see if I wrote it down up here. Yes, you see how we dot it with the n and ds? Remember from last time, we only looked at it briefly, but ds, okay, is the magnitude of r prime dt, provided we can write this as a vector valued function r of t. Okay, so that's what we're going to do. The flux, which was the integral over c of f dot n ds, ends up being the integral from a to b of f of r dotted with y prime over the magnitude of r prime. So let's actually factor that out just to make that a little easier. It's 1 over the magnitude of r prime times the vector y prime comma negative x prime. Okay, so that will be 1 over magnitude of r prime times the vector y prime negative x prime, and then the ds becomes the magnitude of r prime dt. And those cancel, and we end up with the integral from a to b of f of r dot y prime minus x prime dt. So this comes out to be essentially the same exact formula, except instead of r prime, we have some n. This is like our normal n. I tend to call this like an n star. Is our y prime comma negative x prime. Okay, it's kind of like a we've just flipped r prime around, right? It's perpendicular to r prime, okay? So when we dot product this out, right, we're going to get, if capital F is like our usual little f comma little g, this is going to be f of our r times y prime minus, okay, g of our r x prime dt. So the flux integral is often written like this, that the integral over c of f dy minus g dx. Okay, because that's kind of telling you what we're doing here. Whereas, remember, the circulation was f dx plus g dy. Okay, so to compare the flux to the circulation, here's our circulation formulas. Instead of f dot t, of course, we have the integral over c of f dot n ds, which can be rewritten instead of f dx plus g dy. We can say it's the line integral of f dy minus g dx. And it comes out to be the integral from a to b of f of r dot, instead of r prime, it's a flipped around r prime. It's y prime, comma, negative x prime dt. Now, other than this, the mechanics are almost the same, right? We still have to find all the same stuff. We just have a subtly different vector here. So we will look at examples, but I do kind of want to show the difference between the two a little bit. So if you think of circulation along a path, okay, right, if here's our path, if for the most part the vector field F is going along with the path itself, like it could vary a little bit, but for the most part, right, it's going along with the path. This gives us a positive circulation. Okay, if on the other hand, when we make our little path, and the vector field F is the entire time, say, pushing against the path. Okay, and we're going to get a negative circulation. Now, again, this doesn't have to be, it's just like with our normal integrals, right? If you get a definite integral out and it's negative, that doesn't mean the function lives under the x-axis its entire life. It just means that it does for more than it's positive. So same thing here. You could have one little bit that does go with the path, but if the majority of it goes against, it's a negative circulation. Then zero circulation, that's if when you take a look at your path, I'm going to show the two different versions, right? Either the path is completely perpendicular, or it goes along with the path on one side and then maybe goes against it in exactly the same way on the other. Okay, so this would be a zero circulation. So it's either completely perpendicular to C or balanced in a way that it cancels out. Okay, what does flux measure? Well, flux is measuring, like I mentioned, it's how much of the path is perpendicular to it. But there's a little more to it that I like to think about. I like to think of how it measures how much of the vector field is, say, leaving the region or entering. And so what does that mean? There's a little more to it than that, but this measures how much of the vector field is perpendicular to C. Okay, but it can also, other than just measuring how much of the field is perpendicular to the path, it can also give us an idea of how vectors pass along the path. And I think of this as how vectors enter the region versus leave the region. And we got to be careful with this because it's not always region locked, so to speak. But what do I mean by that? Well, if I have my path here, and of course, if the entire path, the entire vector field is perpendicular to the path, right, all the way along, this is going to be a positive flux. Okay, but there's another way to be perpendicular, right? They can be perpendicular, but all the vectors point inwards. So if we make a region, right, and all of the, so here, all of the field is perpendicular to the path, but pointing outwards, right? That gives us a positive flux. Break this off. However, if they're all perpendicular but facing in, this is going to be a negative flux. Interesting, right? So now what gets a little more interesting is those other cases. There are other ways to have positive flux. For example, if I create this path here, and let's say on this side, right, there's some high vectors, like a lot of vectors leaving, quote unquote, leaving this region. And on this side, there's a little bitty guys entering. Well, this would likely give us negative flux, while this would give us positive flux. However, there's more positive flux than there is negative flux. So overall, this would be positive flux. So, in other words, there's more leaving than entering. Okay? Right? There's more leaving than entering. That's positive flux. On the other hand, on this side, suppose that the vectors on this side are, say, entering the region, but on this side of the path they're exiting, but with very small vectors here. All right, this would be another example of negative flux. All right, we have definitely negative flux on this side, but very small positive flux on this side. Okay, so the overall difference would be a negative flux. Okay, in other words, more entering the region than leaving. Right? More entering than leaving. So I'm putting these in quotes because there's, it's not always about entering and leaving a region, because we can find flux over, say, a path like this, right? And it's basically telling us how the vector field crosses over that path versus whether it's entering or leaving a region. But this is how I like to think about it. This is more an intuition thing than a rigorous math thing. And then for zero flux, well, if along the path, say we have a positive circulation, right? A nice, normal, positive circulation, right? Say the path is always tangent to the vector field, right? This would be zero flux. The entire path is tangent to F. So F is tangent to C. So, in other words, this would actually give us a positive circulation, however, it will give us zero flux. Notice here, this gives us a positive flux, but would give us zero circulation. Right? Those ideas aren't always opposites, but they're certainly counter to one another. Okay? And then we have this possibility as well, where, actually let me make this a circle, or as close to a circle as I can. Imagine we have a field that basically always acts the same. Imagine it's pretty much always acts like this. Okay? It's the same as it going in as coming out, right? So here's our negative, here's our positive, but the amount entering equals the amount leaving. Okay? So that's another possibility that could give us zero flux. All right? And given the way I've drawn this, this might also give us zero circulation as well, because just we get as much in every single direction all the way around. So it may actually balance out to give us zero in both. Okay, just to give you an example of how this works mechanically, let's find the flux of capital F equals 2x, 2y over the unit circle. So this was what gave us zero circulation in the last video. Okay, so let's see what happens when we calculate the flux instead. So if we're looking at the unit circle, hopefully we've done this one enough times now that we know that that's R equals cosine t, comma sine t, t going from 0 to 2 pi. All right. Now, just like before, we've got to find our f of r. Right? That part doesn't change for flux. So we're still going to put cosine t in for x and sine t in for y. So we'll still get the vector field, or the vector 2 cosine t, comma 2 sine t. All right. Then we do need to find r prime, but that's not really what we're going to use. Remember, we need to find what I like to call n star, which is the vector y prime, comma negative x prime. So we still need to find r prime, but we just need to flip it. Okay, so r prime is going to be negative sine t, comma cosine t. Okay, but then when we flip it around and whatnot to get our n star, well, we're going to take our y prime. So here's y prime, here's x prime. Okay, so our y prime is cosine t, and our negative x prime will be negative a negative sine t. And yes, I'm writing that like that to specifically show that I'm negating the x. Okay? or the x prime, I should say. And now we just take the dot product, right? So we take cosine t and multiply it by 2 cosine t, so it's 2 cosine squared t. Take 2 sine t and multiply it by sine t, so we get 2 sine squared t. So hopefully we've done this enough times to know that that's just going to be 2. Okay, so the flux, okay, is going to be, well, that's the line integral, f dot n ds, also known as the line integral over c of f dy minus g dx, okay, which is going to be the integral from 0 to 2 pi of 2 dt. Okay, so it's 2 times 2 pi, which will be 4 pi. There we go. We got a positive flux, which we should because, well, this vector field is the explosion field, so at each point, the vectors of f are perpendicular to the path of travel. Okay, let's look at another example here. Let's find the flux of f equals y minus x, comma x over c, which is the quarter ellipse given by this. Well, 3 cosine t, comma 5 cosine t, t going from 0 to pi over 2. That's going to be this guy. We're going to go out 3 in the x and 5 in the y, and this is going to be our path here. Okay, so let's calculate the flux here. So, like always, we need our f. So f of r is going to be f of 3 cosine t, comma 5 sine t. All right, so like always, our x is going to be replaced by 3 cosine t and our y by 5 sine t. Okay, so we'll get the vector 5 sine t minus 3 cosine t, comma, then x, which is 3 cosine t. Okay, so this probably isn't going to be that friendly, but we'll get there. Okay, now we need to find, I'm going to find r prime, but I'm going to be careful to sort of flip it. Okay, so r prime is going to be negative 3 sine t, comma 5 cosine t. Okay, but now we're going to flip it. So instead of r, I want n, let's call it star, which remember is y prime, comma negative x prime. I always like to write it down so I can keep it straight what I'm doing. So y prime, that will be 5 cosine t. Negative x prime, well, that will be negative negative, so a 3 sine t. Okay, now we have the wonderful task of taking the dot product of these two. Right, so f of r dot n star is going to be, well, we'll multiply the x components of these two together. Okay, so this is going to be 25 sine t cosine t minus 15 cosine squared t. Okay, and then we're going to multiply these components together, and we're going to get plus 9 sine t cosine t. All right, so this comes together. Thankfully, here's some like terms. We get 34 sine t cosine t, and we have negative 15 cosine squared t. Now, I want to integrate this. So there are a couple ways we can do that. What I'm going to do is use some identities to help us. So sine t, cosine t, anytime I see that, I always think of sine of 2t. Sine of 2t is 2 cosine t sine t. Right? So what we can do is 34 divided by 2 is 17. So 34 sine t cosine t is going to end up being 17 sine of 2t. And the reason I want to do this is because integrating this is going to be a lot easier than integrating this. Same thing here. With a cosine squared, we're going to use the half angle formula for cosine, which tells us that cosine squared is 1/2 plus 1/2 cosine of 2t. Right, so this is going to make our lives a lot easier when we try and integrate this. Okay, so we will get 17 sine of 2t minus 15 halves plus 15 halves cosine of 2t, and I think now we're ready to integrate. Right, so the flux is going to be the integral over c of f dot n ds, okay, which will be the integral from 0 to pi over 2, right, so that comes from here, since we're only doing the quarter of the circle, okay, of this monstrosity, 17 sine of 2t negative or minus 15 halves plus 15 halves cosine 2t dt. All right, almost there. Now we just integrate. Integral of sine of 2t is going to be negative 17 halves cosine of 2t. Okay, integral of 15 halves is just negative 15 halves t. And then the integral of cosine 2t here, that's going to be plus 15/4 sine of 2t. And we'll evaluate this from 0 to pi over 2. Oh my goodness. Well, this seems terrible. Hopefully it won't be. Okay. When we plug in pi over 2, our 2t's are just going to become pi. So we'll get negative 17 halves cosine of pi minus 15 halves times pi over 2, okay, plus 15/4 sine of pi. Okay, well, thankfully, we already know that goes to 0. And then this is negative 1. So it should hopefully simplify a little bit. So there's plugging in the pi over 2. This case, we do need to plug in the 0 because of the cosine. We'll have 17 halves cosine of 0, then minus 0 plus 0. All right, so we're going to get 17 halves. Then here we're going to get minus 15 pi/4. That's 0, minus a minus here, so we're going to get plus 17 halves. So we get 17 minus 15 pi over 4. And let's see what that ends up being from a calculator. All right, I got that's about negative 6.56. Let's see if we can take a look at this on a graph and see what we... Oh, whoops, I totally plugged that in the calculator wrong. Hang on. That actually comes out to be 5.219-ish. Okay, that's better. That looks better. So when we jump to the graph, if we look at what's happening here, so here's the path, and here's what this vector field looks like. And you'll notice we have here on this side, some of the vectors seem to be quote-unquote entering the field. But as we move along, suddenly these maybe look like they're lined up, and then suddenly now they're all sort of pointing outwards. And then this one seems to be completely going against the path there, so that would give us some negative circulation, but it's some zero flux. But along So around here it looks like they're entering, but then they swap. So it does look like for most of the path, for more of the path, vectors are quote-unquote leaving this region. Okay, and what region am I talking about? Well, imagine if the ellipse went all the way around and we're talking about leaving the region itself. Okay, so that is essentially what the flux gives us. Okay, now I want to take a step back to circulation for a minute. So now that we've looked at how flux works, we're going to focus more on circulation for a while, but flux will come up again later. Anyway, I want to look at the circulation of F and G, these two vector fields, so that look very similar, right? I want to look at these two over two different paths. So notice that these paths both start and end at 0, 0 and 1, 1. So let's call the first one C, which is simply y equals x, and it's the line segment from 0, 0 to 1, 1. And we've talked about this one before. That's going to be the vector valued function t comma t, with t going from 0 to 1. Okay. All right, now this other path is the parabola y equals x squared from 0, 0 to 1, 1. And actually, this is also a very simple vector valued function to make. If you already have the formula y equals x squared, just make it t comma t squared. Okay, from t going from 0 to 1. All right, there are other ways to do this, but this is the simplest, so that's the one we're going to use. Okay, so here are our paths. Instead of calling this C, let me call this D. So I have C and D, R and S. All right, so let's look at F first. So I want to look at the circulation of F. Okay, I'm going to write it down again here. It was xy comma 1/2 x squared over C and D. Okay, so for C, we have our R. I'm not going to write it again. We have it up here. So our R prime is 1 comma 1. That's nice. And we also need F of R. Also not too bad. That's going to be F of t comma t. So we're just replacing both x and y with t's. All right, so we're going to get t times t, so t squared here, comma, and here 1/2 t squared. All right, then we need the dot product. Okay, so it will be this vector dotted with the vector 1, 1. Well, that's not going to be that bad. That will be t squared plus 1/2 t squared. So that will be 3/2 t squared. All right, and then from here, the circulation over C will be the integral f dot t ds, or the integral from 0 to 1 of this thing, 3/2 t squared dt. Okay, so when we integrate this, thankfully the 3 is going to cancel, so we'll actually just get 1/2 t cubed from 0 to 1, and we get 1/2. All right, so now let's take a look at the circulation of F over D. So D, let's see if it's still on the screen there. There's our S. All right, our S is t comma t squared. So what we need is our S prime, which will be 1 comma 2t. Okay, then we need our F sub S. So that's going to be F of t comma t squared. So this one's a little, I won't say necessarily it's tricky, but you know, it's not as hard to make mistakes as f of tt, right? So our x is going to be t, our y is going to be t squared. Okay, so for xy, we're going to get t times t squared. Here just showing what I'm doing. And then 1/2 x squared. Well, it'll be 1/2 t squared. All right, so now we need to take the dot product of these two. So f of s dotted with s prime is going to be, let me write them out again, the vector t cubed, comma 1/2 t squared, dotted with the vector 1, comma 2t. And we're going to get t cubed plus 1/2 t squared times 2t. Well, that's going to be 2t cubed. All right, so the circulation over d will be the integral over d of f dot t ds, which will end up being the integral from 0 to 1 2t cubed dt. Okay, when we integrate that, the integral of 2t cubed is going to be 1/2 t to the 4th, evaluated from 0 to 1, so we get 1/2 again. So here's the question. Is this always true? Right? The circulation of f over this path, so this was c, was 1/2, and the circulation of f over over d, the second path, was also 1/2. So a natural question, is this always true? Well, let's see if we get the same thing when we look at G, right? If we do the circulation for G. Okay, so the only real difference here is in the y component, instead of a 1/2 x squared, we have a 1/2 y squared. I went ahead and copied the information that we're going to reuse, right? We still need r prime and s prime to do this. So in this case, g of r is going to be g of t comma t. Well, that will end up being the same thing. We'll have the vector t squared and then 1/2 t squared. Okay, so then when we take the dot product, we get the t squared plus 1/2 t squared. So we end up with 3/2 t squared again. So we should get the exact same circulation. So the circulation over c here will be the integral over c of g dot t ds, which will be the integral from 0 to 1 of 3/2 t squared dt. I'm not going to work through that again. We should get 1/2. It's the same integral. Okay. Now let's see what happens when we do this over s. Okay, so g of s, that will be g of t comma t squared. So once again, our x is getting replaced with t and our y with t squared. Okay, so this will be same thing in the first component. xy will be t cubed. However, in the y component, we have something different. It's 1/2 y squared. So it's going to be 1/2 t squared squared. So t cubed, comma 1/2 t to the 4th. All right, when we dot this, it's going to be 1 comma 2t dotted with t cubed. I didn't do that in order, but thankfully for the dot product it doesn't actually matter that much. So we'll get t cubed and plus, this will be, the 2's will cancel, And so we'll get t times t to the fourth, so it will be t to the fifth. Okay, so then the circulation over d will be the line integral over d of g dot t ds. So that will be the integral from 0 to 1 of t cubed plus t to the fifth dt. All right, we're almost to the point I'm trying to make. When we integrate this, I'm going to get 1/4 t to the fourth plus 1/6 t to the sixth. And we just evaluate that from 0 to 1. So it's 1/4 plus 1/6, which comes out to be 5/12, which is not equal to the 1/2. So the circulation for G does not line up. So for G here, we also get 1/2. But here, for G, we don't. We get something different. The circulation of G over D is not 1/2. It's actually equal to 5/12. So what is happening here? Okay, we can't say that the line integral starting and ending at the same points, no matter what path we take, we can't say the circulations are always the same, but maybe sometimes they are. Let's take a look at what's happening with these vector fields. Okay, so here is F. And you can see that F actually, it's not exactly graphed perfectly, but you can see how nice and balanced it looks, right? And if I put my two paths here, you can almost see how uniform it kind of looks around these paths, or just in general. So if I graph more of the vector field here, you can kind of see how balanced it looks around the origin. As much as it's coming in this way, it's coming in this way, and then it's feeding out that way. It's a nice, balanced, nice-looking vector field. Okay, let's look at G now instead. Okay, G does not have this property, right? We have some coming in this way, then it flips out to going outwards that way. It doesn't have the same sort of nice uniformity, although some may argue it does seem to balance, but maybe not in the same way, because a lot of the directions are opposing versus what we saw with F. So a question then becomes, well, what's going on here? What is the main difference between these fields? Okay, why are my vector fields behaving this way? And if we sort of zoom in on the paths that we were actually concerned with, okay, let me up the scale a little bit. You can see in this case with G, there's a lot more magnitude going on earlier along, like a lot more activity going on along in our first path than on the second. Okay. All right, so to answer this question, we actually need another tool. So we are going to answer this question in the next video, and that has to do with what we call conservative vector fields. What's happening here is that F is conservative and G is not. G is close to being conservative. It's kind of conservative-ish, but it's not. Okay, so in the next lecture, we will talk about what those things mean and how they can actually simplify our lives when it comes to finding line integrals. All right, so I will catch you all on that one. Cheers, folks.